In this online class, we are going to see magnetostratigraphy. The magnetostratigraphy is based on the magnetic polarity reversal, and it is applied on rocks, frequently on lava flows, deep sea cores and on sediments. What kind of sediments? It can be deep sea, pelagic limestones, and also in the calcareous ooze. They are recovered by the ocean drilling processes. Magnetostratigraphic study has yielded the geomagnetic polarity time scale, in short GPTS, and this has been integrated thoroughly with other stratigraphic approaches such as chemostratigraphy involving the chemistry of the rocks, chronostratigraphy involving the geochronologic dating of the rock, biostratigraphy, which means stratigraphy established based on fossil studies. What is the time range within which the GPTS has thoroughly been established? It is from late Mesozoic to the Quaternary time, and this has direct input on the geological time scale. So, the geological time scale, what I have already presented, has integrated magnetostratigraphy, chemostratigraphy, chronostratigraphy and biostratigraphy. It is, we can call, grand compilation to understand the earth history. If we look into the history of magnetostratigraphy, Brunhes as early as 1906 attributed opposite magnetic polarity of rocks due to the local anomaly. The explanation was not very clear cut why the magnetic polarity reversal is found within the rock. 1950 onwards, the modern era of studying geomagnetic reversal started, and 1960s was the time when geomagnetic field reversal was properly established. This is also the time when the Hess theory of sea floor spreading and the major push for the continental drift theory came. Rocks of same age has the same polarity has been a long standing observation by the geoscientists. In this presentation, at some point, shivalik sediments will be shown to have studied for the magnetostratigraphy. Magnetostratigraphy is a short form of the magnetic polarity stratigraphy. Rocks can consist of magnetic minerals, and magnetic property of the present rock and the past rock can be utilized to create a stratigraphic succession. We will see how it is done, and then that succession will be possible to correlate globally. Now, from where the Earth's magnetism comes, here we will do things briefly, we will not get into great detail. From geophysical studies, we know that most of the Earth's dense core is consisting of iron, and the density of the core is around 10.72 gram per centimeter cube. Now, this core can be divided into two parts, the outer core and the inner core. The outer core of the Earth is fluid and it moves. Its movement creates magnetic field, and essentially the Earth behaves like a giant bar magnet. Now, we have to understand that not only the Earth's outer core is fluid and it moves, we know that the asthenosphere of the Earth also is a fluid and it moves. The Earth's magnetism is not coming due to asthenospheric movement, rather from the outer core's movement, that the asthenosphere, which is usually below 100 kilometer, its movement leads to plate movement. Several views are there, the different kinds of convection pattern of this asthenosphere, which we are not getting in. I emphasize here asthenospheric movement. To the present state of knowledge, we do not think that it produces the Earth's magnetic field, rather the liquid outer core of the Earth moves in a certain pattern which has been modeled, and it produces the magnetic field. Essentially, the Earth behaves like a giant bar magnet. Now, the geographic north and the geomagnetic north do not match with each other. The geographic north in the Earth differs from the geomagnetic north. the convection pattern of the outer core, the dynamo changes for unknown reasons. We do not know why exactly, how exactly the convection pattern, the movement pattern of the outer core material changes, but when it changes, the north and south magnetic poles switch their positions. What does it mean? If I take a magnetic needle and say this is north and this is south, with a thread I have put a magnetic needle, then the north direction always orients in a specific direction at present and the south is in opposite direction. But imagine that the outer core's convection changes. What will happen if it happens right now instantaneously? This needle will orient just in opposite way. In the earth history, the magnetic polarity reversal has happened, and based on the study of the rocks, we have interpreted several such transitions. On average, the magnetic field reverses about every 5 multiplied by 10 to the power 6 years, or after every 5 million years. We do not know why exactly after around 5 million years the switch happens, why the outer core material moves differently, so that this magnetic field reversal happens. And in fact, if we look at the earth history, at least from the Jurassic till today, we know that this age 5 million year itself also varies sometimes. We will see in more detail. Now, if the earth's magnetic field changes, north becomes south and south becomes north, it becomes a global incident. Worldwide, we will see when the rocks are forming, they will acquire that magnetism. So, if anything happens in the Indian Ocean in terms of the geomagnetic reversal, of same time we should get the geomagnetic reversal in other parts of the world. So, it is a global event and it is good for correlation. The geomagnetic reversal can prove catastrophic for the organisms, can lead to catastrophe for organisms. We use two terms, normal polarity and reverse polarity. What is the meaning of normal polarity? At present, you put a magnetic needle and you find that the one part of the needle is always pointing towards the magnetic north. That one, what is at present, is known as the normal polarity. And imagine with a time machine we would have gone to the past and the same magnetic needle is oriented. What was earlier pointed in the north direction, that direction will get switched, and we call that as the reverse polarity. We represent normal polarity with a black box and the reverse polarity by a white box. Now, this transition from normal polarity to reverse polarity is not instantaneous. So, there can be a geological time period when the transition happens, and the transition phase is represented by this box. Now, we are going to see how the correlation will work. It is a simple way of presenting to the beginners. Here is in the geological time scale, imagine this is a rock record, or from the rock record we have drawn this conceptual rectangle with some shaded zones. So, this white portion will indicate a reverse polarity, this white portion indicates a reverse polarity, this is a reverse polarity and this is a reverse polarity, and this shaded region represents a normal polarity, this represents a normal polarity. If we know the absolute age by dating the rock, which I will be discussing in the chronostratigraphy in detail, then we may be able to correlate this normal polarity in the past with that normal polarity. Therefore, these red lines show the correlation, and immediately below this normal polarity, this reverse polarity may be correlated with that one, and the reverse polarity here above the normal polarity zone may be correlated with that one. Now, from this normal polarity to the reverse polarity, there can be a transition zone. I said the transition zone is presented in this way. So, I can draw this transition zone here. So, it may be possible that such correlation may be made, and here from reverse polarity to the normal polarity there can be a transition zone. So, this also, and here also one, and this can be correlated. Now, not always between two basins one magnetostratigraphic layer can be correlated with the other in the other basin. It may be possible when one basin sedimentation was happening throughout, so normal reverse polarity change has been documented, but in the other basin there was a gap in sedimentation, or whatever sediments came and the polarity got recorded, that got eroded. So, not always such correlation can simply be made. Another point, such a magnetostratigraphic column, it may be possible that we have more than one normal polarity zone. So, here we have got one over there and the second one. We are not sure in that case whether this correlates with this one or this correlates with that one. The question is which normal polarity zone will be matched with that one. In fact, in absence of absolute age of the rock, this becomes practically very difficult. And even if the chronostratigraphic data is not there, suppose the age is not available, then at least the biostratigraphic data can be used to link, say, this one with that one. Here, suppose some index fossil was found within the rock and the same index fossil has been found from here. So, we understand, okay, this will be correlated with that one, and its continuation in the other basin suppose is not found. So, we can say that possibly it was there and then it got eroded. Are we getting an unconformity over here? If any unconformity is found, then we can say there was sedimentation where this normal polarity was recorded, but then it got eroded, or in other words there was a gap in sedimentation. So, this normal polarity was not at all recorded. The switch from normal polarity to reverse polarity or vice versa is not instantaneous. It can take 4000 to 5000 years, which means that organisms can have sufficient time to slowly adapt with the new geomagnetic field. So, all the organisms will not get extinct, but some may get adversely affected. And if the geomagnetic reversal is instantaneous, imagine it is very fast, few years, although it is not so, then there will be a large scale extinction of organism, because organisms cannot adjust so fast in few hundreds of years in an opposite magnetic polarity. And this process of reversal, what I said, can usually take 4000 to 5000 years, will be represented in the magnetostratigraphic column by such a domain. Some numerical data, the present magnetic field, that means the normal magnetic field at present has been there for the last 7 multiplied by 10 to the power 6 years, or 7 million years. When we look at the older rock records, very old rocks becomes difficult to interpret for magnetostratigraphy. Pre-Carboniferous nature of magnetic field is not well understood, partly understood but not very clearly understood, and most of the information of magnetostratigraphy comes from the seafloor rocks, and we need to understand why it is so. Consider a mid-oceanic ridge from where batches after batches lavas are basaltic lavas coming up, and they are getting deposited at the sides, and as the new lava comes, the old layer actually is pushed away. This is a typical textbook diagram. Here we have old batch of basaltic lava, and then the newest batch is here, and here we have got the third one. When this lava is coming and spreading at both the sides, it can acquire the Earth's then magnetic field, normal polarity or the reverse polarity, and it gets preserved. However, we know that the sea floor gets destroyed due to subduction process. one plate can subduct below the other one, and the subducted part goes to the asthenosphere and becomes difficult to trace. So, very old oceanic crust does not exist. In fact, the oldest seafloor rock preserved is late Jurassic, which is around 160 million year old. So, our information of magnetostratigraphy from the marine rock is coming from 160 million year onward. Onward means and younger. This is the domain where we have a better magnetostratigraphic record. Now, while we are dealing with the marine crustal rocks, there are certain gaps and overlaps in the magnetic anomaly. We can prepare the magnetostratigraphic table, and there can be some gaps and overlaps, and how they happen because of the ridge jump, because of the geological irregularities, and because of the change in the oceanic plate velocities. Because of these, while we are preparing the magnetostratigraphic column, we may get a good information over here, we have no information over there. So, this is a gap, and then again a good information. So, this is a zone of gap, or it may be possible because of these complications, ridge jump, geological irregularity or oceanic plate velocity change, that we prepared good amount of information from here, and then again from another rock sample we get data for this place. By doing that, we find that there is an overlap. Now, the magnetostratigraphic table needs to be corrected. If there is a gap, look at other stratigraphic records in other oceans crust, whether you have a data here or not, and if the overlap is understood, you have to avoid this overlap, this information which has got duplicated. We will see more about the magnetostratigraphy. We need to now look at a few basic things about the remnant magnetization, and then we will again initiate the magnetostratigraphic discussions. How a rock attains normal and reverse polarity? It is attained at the time of the rock formation. So, here when we are discussing the remnant magnetization, we are essentially talking about the primary remnant magnetization. Now, the principal magnetic phases carrying significant magnetization are the FeTi oxides, and we can think of two solid solution series. One is the Magnetite-ulvospinel, which is Fe3O4, Fe2TiO4, and hematite-ilmenite, which is Fe2O3, FeTiO3. Fe3O4 is the formula of magnetite, ulvospinel the formula is Fe2TiO4, hematite formula is Fe2O3, and ilmenite formula is FeTiO3. Note that in magnetite, iron is to oxygen is 3:4, and in hematite Fe is to O is equal to 2:3, and from here we can understand that the Fe by O ratio is higher for magnetite than hematite, and we know that magnetite is more strongly magnetic than hematite. Another point regarding the solid solution, Fe3O4 can be written as Fe2FeO4. Now, Ti can completely replace this Fe, leading to the formula Fe2TiO4. So, here Ti has 100% replaced this Fe, but as I am talking it is a solid solution, Ti can partly replace this one place of Fe. Similarly, hematite Fe2O3 I can write as FeFeO3, and this one Fe can be replaced by Ti, but instead of 100% replacement, a partial replacement is also possible, and that is the meaning of the solid solution series. So, these are the principal magnetic phases within the rocks, and these are the mineral names. Now, the minute grains of magnetic minerals act like tiny bar magnets. It can be a subcircular grain, but it can be conceptualized as a bar magnet with one as the north and the other side as the south. Note that heat destroys the magnetization of the rock. So, if the rock is heated, a magnetic rock can become non-magnetic, or a magnetic mineral, if it is heated too much, it can lose its magnetism. And we know from the data set that the magnetic minerals lose magnetization usually at more than 500 degrees centigrade. This is an average value, and that is what is said is in most cases, and this temperature is called the Curie point. What is Curie point? It is a temperature beyond which a magnetic mineral becomes non-magnetic. For example, for hematite it is 650 degrees centigrade, and for magnetite it is 580 degrees centigrade. So, we can see that magnetite's Curie point is less than the hematite's Curie point. Now, with this basic idea, we will see the three kinds of magnetization. We start with the thermal remnant magnetization. Molten rocks cooling below the Curie point captures the then magnetic field and it gets locked within it. Since we are talking about the molten rock and its cooling, we are essentially talking about the igneous rocks. We are not talking about the metamorphic and sedimentary rocks in this case. Imagine there is a partially molten material at 850 degrees centigrade, and for this rock the Curie point is, I give some number, 572 degrees centigrade. Now, this melt is cooling, and when it crosses this 572 degrees centigrade and goes at a temperature less than 572 degrees centigrade, what happens? When this transition was happening, there was Earth's prevailing geomagnetic polarity. Either it was normal polarity or the reverse. The rock captures that geomagnetic polarity when this transition was happening, when 572 degrees centigrade temperature was reduced. So, now if at present we study this rock, igneous rock, which has cooled from above Curie point to below Curie point, we will know when this transition happens, the Earth's magnetic field was normal or reverse. While discussing the blocking temperature, one point is to be understood: when lava comes in contact with sediment, the temperature in the sediment can cross the blocking temperature of magnetization. Suppose this is a hot igneous molten material that has cut across the sediments as a dike, and near this dike there will be a zone within the sediment where there is significant temperature rise. Now, this temperature rise at the periphery of the dike can cross the blocking temperature of magnetization for the sediments, and so long this portion of the sediment cools down can acquire the magnetic polarity prevailing at that time on the earth. So long the baked zone cools and the temperature is falling down, before it falls down below the blocking temperature, the baked zone, this zone can acquire the then geomagnetic polarity. So, which means that in this portion the geomagnetic polarity and in this portion may vary. So, also in this zone and in this zone. When we are dealing with a single mineral, it can have a single blocking temperature, but when we are dealing with a rock with different minerals, each one has their own blocking temperatures. Therefore, for rocks, instead of a single blocking temperature, a blocking temperature spectrum exists. This is that blocking temperature spectrum. Let us take the detrital remnant magnetization. Here the tiny magnetic sediments, note we are using the word sediments. What can be the size of these sedimentary grains? They can be only few micrometer in diameter. Note, diameter is a word more close to the near circular or circular grain size. And what happens? These magnetic sediments act like bar magnets, and that is what I said. Although the grain can be nearly circular, effectively geomagnetically it acts as a bar magnet, and they align with the magnetic field as they settle through the water column. So, here we are essentially talking about these sedimentary rocks, and not all sedimentary rocks. In fact, sedimentary rocks deposited in water, number 1. Number 2, that there are distinct grains that gets deposited. So, we are talking about clastic sedimentary rocks. In this definition, strictly speaking, the non-clastic sedimentary rocks such as limestone is excluded. Nearly spherical grains that were depositing in the water, when they were depositing, earth had at that moment a north-south polarity. Those sedimentary grains, tiny grains, also acquired that same north-south polarity. In turn, the entire rock attains a magnetic polarity, and this is a time when the settlement happens. However, there is a word of caution. After such grains got settled, there can be overburden pressure and diagenesis, and that can partially destroy the rock's magnetization. This has also been reported. So, I can write here, diagenesis can at least partly destroy rocks. So, this means if we are dealing with unconsolidated sediment or semi-consolidated sediment, its magnetization property will be better than a sedimentary rock which has undergone adequate diagenesis. So, here what kind of rocks we excluded in the discussion? We have excluded metamorphic rocks and we have excluded igneous rocks. In thermal remnant magnetization, what did we exclude? We excluded metamorphic rocks and we excluded the sedimentary rocks. Let us look at the detrital remnant magnetization. What kind of minerals in sediments are common carriers of DRM? The answer is magnetite. The formula is Fe3O4. Then titanomagnetite, which is a solid solution between ulvospinel, which is Fe2TiO4, and magnetite Fe3O4. These are the two end members of a solid solution series. At one side is the ulvospinel Fe2TiO4 and at the other end is Fe3O4 magnetite. In between there can be minerals of different compositions. We can look at the formula of Fe3O4 in this way, Fe2FeO4, and think that this position can be partly or completely replaced by Ti. For example, if I replace here Ti, it becomes Fe2TiO4, which is the formula of the ulvospinel. Now, in different proportion there can be Ti replacement, and depending on that the solid solution series can be defined. When we say that the DRM takes place, we do not mean that the alignment of the mineral grains are happening in the water column. Only after they settle the DRM develops. At what depth range the lock-in of DRM happens? It is generally 10 to 20 centimeter from sediment water interface. Suppose this is the place where sediments are deposited from water and this is a sediment layer, then this can be called as the line of the sediment water interface. Consider this is the water column. So, when we say 10 to 20 centimeter, that is counted from here downward 10 to 20 centimeter. This 10 to 20 centimeter is not from the water column, no, neither is this one. And as more and more sedimentation happens, the sediment water interface actually moves upward. So, after some time, say this was starting at T1 time, at T2 time more sedimentation has happened and then this becomes the sediment water interface. Then this 10 to 20 centimeter lock-in depth will not be defined from this T1 horizon, rather from this T2 horizon. So, from here 10 to 20 centimeter, which means if I take this basement as static, the lock-in depth of DRM with more and more sedimentation ideally moves upward.